Today we have Charles Wang to tell us in two parts about Newton-Okounkov bodies, minuscule homogeneous spaces, and beyond.
Yeah, so first I would like to say, on the first part, I'll probably say not too much about this, but I would like us to become very familiar with a few simple examples. So, describe these in a few different ways. And this will be for non-expert. I think many people already know many of these things, but I would like to.
K4?
K4, or K trace.
So weird.
So I'd like to explain very explicitly how I think about these things, and then hopefully in the second part of the talk, we'll get some examples out of these. Right, so maybe the first definition you see of these things is that you should think of GR4 as the set of V, dimension V is K, and let's say V that's inside of C4. So everything will be complex. Right, it has natural Kluger coordinates. Given by the K by K minors. Any matrix whose rows span V, so I'll just call that representative. Right, so I'd like to spend a bit of time thinking about where these actually come from and why we define it like this. So in yesterday's talk, we saw this kind of representation. So we saw that GR K N for now, that's the K wedge of Cn. And if you have some space V, which is spanned by V1 to Vk, and then you send it to the wedge of these guys. So how does this lead to Kluger coordinates? Well, if you expand each VI, Vj, okay, and then you just follow along and do the same expansion in the wedges, okay, you'll come up with Kluger coordinates. Right? So for a very simple example of this, if you have GR24, and maybe I just take a very simple space for now. And you just want to do. And if you want, let's write E1 wedge E2, and in this talk, I'll write that as E1, 2. All right, so it only has one non-zero Kluger coordinate, which is the coefficient of E1 wedge E2 here. Fine. Now, to take a step back, the first question we might ask is, why do we think about this wedge power? So why wedge K, Cn? And then maybe the second question is, why is it so natural to expand it in terms of the standard basis here? Right. So answer the first question. So it turns out that sometimes you want to think about this Gaussian in okay, so I guess slightly different way. Okay. You'll think of it as a quotient of some big matrix group. So SLN mod something like this. But first I'll think about just this matrix group SLN. So if I look back over here, well, SLN has a natural action on Cn, which also extends naturally to an action on the wedge spot. So if you write it this way, it turns this thing into an irreducible representation. Of SLN. And we try to analyze the structure of such things. So you want to understand how the irreducible representations of any group like this, any matrix group, looks like. And maybe the most common approach is that you find a large abelian subgroup. you act on its representation by that abelian subgroup. So you then decompose the representation into a bunch of one-dimensional representation, and then you figure out how the rest of the group acts. So find the largest abelian subgroup, decompose. 1D subgroup or abelian subgroup. And then you figure out the rest of subgroup. Okay, in other words, what does it do to these one-dimensional subrepresentations for your abelian subgroup? Right. So I'd like to give some explicit examples of this. Okay, so this thing is an irreducible representation. And the reason that this basis is so nice is that often you choose your abelian subgroup, T for maximal torus, just be diagonal matrices inside of Ln. Well, you ask, well, okay, so this is a nice abelian subgroup, and you ask, how does this abelian subgroup act on these wedge powers? So how does Cn? Well, it's very nice. Okay, so it has a bunch of simultaneous eigenvectors. Which are exactly the wedges of the standard basis vectors. Okay. So anytime you have eigenvectors, you might ask what are the corresponding eigenvalues, and in this context, it's called weights, or torus characters. Okay. Just telling you which entries you should take from your diagonal matrix. Right. I'm presuming many people or most people have already seen this, but are there any questions about this setup so far? So I'd like to go and look very specifically for GRK4. So I said K was 1, 2, or 3, so we should have these irreducible representations. So wedge 1, C4, which is just copy of C4, wedge 2, C4, and wedge 3, C4. And I'd like to take a second to think about how these things kind of break up into these smaller pieces. So we've drawn some examples. So here I've given each one of these representations, so C4, second wedge, third wedge. I've written down the standard basis decomposition, so E1, E2, E3, E4, just the standard unit vectors inside of C4. E12 means wedge E1 of E2. E13 is E1 wedge E3, and so on. And so at least labelings of these points in these graphs refers to the weight basis, or these simultaneous eigenvectors, for the torus action of diagonal matrices. So it turns out there's a bunch of other data that you can get as well, and that's what I'll be mostly interested in today. So next to each of these things, I just labeled them by the corresponding weight. Okay, so turns out that there are something called fundamental weights. Which you can use to express all others. So if you think about it in terms of torus characters, you might say, well, you have some variables which generate the polynomial ring. If you think about it in terms of the Lie algebras, you think about some basis of weights here. Okay. And so next to each one, I've also written the corresponding weight as a sum of fundamental weights. So this E1 up here has weight fundamental weight 1 plus no other fundamental weights. Next one has minus fundamental weight 1 plus fundamental weight 2, and so on. Okay, so IJK here in the picture. I'll call these pi I today. Oh. Okay. only 2 times 1 plus 2 plus c. So fine. As well, there's one more piece of data. So in this particular example, you can think of the labels of edges in these graphs as telling you, say, which permutation you have to act by, or which simple transposition. 3, 2, 1. So if you act on the labels of these standard basis vectors by the corresponding permutation, you'll get exactly these actions. Okay, so that doesn't work in general, but for these nice cases, it turns out to be enough. Yeah. Sorry. Any questions so far?
What is the number of the edges?
So the number on the edges you can think of in this particular case as telling you if you act, for example, on E1 by S1, it switches the first and second coordinates. So it takes E1 to S2, E1 to E2. And you can analogously for that. Maybe more precisely in this picture, you could think of it as the Chevalley generator Fi acting on the corresponding polytope. Okay.
So are these just crystal graphs?
These are crystal graphs in this case, although they're slightly different from crystal graphs in general. So these are minuscule representations, so you won't see the difference, but if you go beyond minuscule cases, you'll see that there's some difference. But usually I think of these as the weight poset. So you get some set of weights from your representation and you pick some natural ordering on them, giving a poset structure. Right. Great. Okay, so the final thing I want to say about this picture here is that if you just look at the SL4 example, and I'll say just the span of E1. This thing is maybe not quite the right thing to think about, okay? Because SL4 has some elements fixing this thing. Okay. So up here we promised that there was some kind of embedding these Grasponians, but so far we don't have such a thing, because if you just take SL4 and you act on span of E1 or you act on E1, you get a very non-injective thing. So there are many different elements of SL4 which can map to the same thing once you act on these like vectors. So how do you fix this? Well, you look at what the stabilizer of the action on E1 is. Okay, so if you write down some matrix in SL4, a 4x4 matrix. You can try to find out which elements stabilize this vector or stabilize the span. In other words, who sends this back to itself. And turns out, well, okay, you just sit down carefully. It's exactly matrices of this form. So invertible matrices with determinant 1, which have this format. Right? So E1. So such things are called parabolic. So they stabilize the highest weight in some irreducible representation of G with SL4. And so instead of trying to embed SL4, what you should really embed is the quotient of SL4 by this parabolic subgroup. Okay, you can embed it into the projective space over C. What you do is if you have some representative here, just send it to the action on the highest. So since we mod out by the stabilizer of this highest weight, then we get an actual honest embedding, and this is the usual Plucker embedding. So similarly, on UK embeds into a competitive space like AC. Okay. Any questions about that? So when I think of it coming from this representation, I tend to think about the Kluger coordinates in a slightly different way. Okay. So of course you can still think of it in the same way. You just expand out each one of these wedges into the corresponding wedge of standard basis vectors and then find the coefficients. Those are the literal Kluger coordinates. But when I write it like this, normally I think of it as the following kind of projection operator. Coordinates of projection operators. So you start from the highest weight and you think of it as a function as follows. Okay, so for example, let me just write one of these here, maybe p minus 101. I want to say what the Kluger coordinates for a particular g are. What I do is I'll look at the corresponding standard basis vector. So E23 dual action g times E12. Okay, so this is inside of S or mod. So I take this weight basis that I found, this basis of simultaneous eigenvectors for the diagonal matrix action. I take the dual basis for this basis here. And then I write each Kluger coordinate as a kind of projection. So it just picks out that individual coordinate when you expand your wedge. So it's nothing but a restatement here. But this will be how I think about Kluger coordinates for the rest of this talk. So let me pause for any questions about that.
What is written there? E23
dual.
G dot E12.
Yeah. So if you want to find the Kluger coordinates of some matrix G, you act on the highest weight vector, and then you pick out what particular coefficient you want. So the Kluger coordinate corresponding to this weight minus 101 just takes E23 dual, takes the coefficient of E23 and the expansion of G acting on E12. Any other question?
Sorry, what does negative 101 correspond to 2?
So this just means which weight this is. So if you express the weight of this eigenvector in terms of fundamental weights, you'll see that it's minus first fundamental weight plus third fundamental weight.
Okay.
The fundamental weights are like T1 plus T2 plus up to Ti.
Yeah, exactly. In principle, you don't have to fix such choices, but yeah, since I already chose the diagonal matrix. Yeah, so the literal coordinate expressions of the fundamental weights can change based on your choice of torus and how you choose to parameterize it, but yeah, that would be one standard one. Okay. So let me go back to this picture for just 1 second. So I said that these were posets. So if you study the SO4 action on these simultaneous eigenvectors for diagonal matrices, you get a natural poset structure as well. And here I've drawn the Hasse diagram of these posets. So it turns out, okay, so in very nice cases, let me put this in quotes. So there's just a finite list, so I could just write it out and tell you, okay, it's equivalent to this adjective minuscule. But let me not worry too much about this definition. But anyways, in very nice cases, turns out that the poset of weights okay, so in other words, if I just take this poset over here, the one that you get by the G action, and the poset of weights is a distributive lattice. Okay. So fine, just some order theoretic term. But what this buys you is the following nice statement. So it's a fact about distributive lattices. Okay, so if L is distributive lattice, Then L is isomorphic. The that order ideals. Let me take filters for today. Order filters of the coset. Join your useful elements. So that's just a very nice combinatorial characterization of these things. But let me actually give examples in this case to say what these are.
Can you remind us the definition of coset of weights?
Yeah, so it's just these posets. So all you do is you take the weights, and then you have to analyze the SL2 actions inside of G, and you get these Chevalley generators. And so if you start from the highest weight and you just figure out how you can act by all the Chevalley generators, that gives you all the other weights with a natural ordering on them. Where if you act by F, that lowers the weight.
So in the very nice case, we are considering all the weight spaces are one dimensional.
Yes,
These are elements of your coset.
exactly.
Can you read the thing in the part, the order something of the poset?
Order filters of the poset of join irreducible elements of the lattice L.
They're like up closed or down closed.
These are up closed. Yeah, you can also do down closed dually, but. Right. So I'd like to give the examples in this case to say what these subposets are, what the order filters are, and how we interpret them. Right. So let me start in the leftmost example, so C4. So join irreducible means you cannot be written as the join of two other elements. So let me just define this really quickly. So join irreducible cannot be written. Do one more other elements. Okay, and at least in a finite poset, an equivalent condition is that there's exactly covers one element. So in other words, if I go back to these posets over here, I'll just circle all of the weights which cover exactly one other weight. In C4, there are these three.
Convention is the minimal element is not.
Yep.
Fingers.
Okay. In wedge 2, I'll circle these. Right, and then analogously. So according to this definition of distributive lattice, I'm supposed to take those things, the circled red ones, and consider them as their own poset, and then look at order filters of it. Right? Let's see, for example, let's take this poset here. Wedge 2, see for example, diamond poset. Okay, and then in wedge 3, C4, again, I have the straight line. Okay. And now, for no reason, I'm going to draw boxes around these. And if you squint a little bit, these are exactly Young diagrams. So in this case, this is, well, maybe these should be slightly differently oriented. Maybe I actually tilt them, but okay. So you can think of this as 1 by 3 Young diagrams. They're 2 by 2, and these are 3 by 1. So in each case, you get K by 4 minus K Young diagrams. And now we ask, what are the order filters of these things? Okay. So. All right, so let me take the interesting example. So that's the one with the diamond shape. Okay, I'll just write the ordering here. So what are the order filters? These are the up closed sets. So order filter.
Blue is hard to see.
Oh, sorry. Thank you for telling. So just to define an order filter now. Up closed cells. Equivalently, I just set F its order filter. Here, X, F, Y, X implies Y. So in other words, a subset of this poset is an order filter if anytime you go up, you still contain the element. So this thing has 6 order filters. So empty, single box, like this, this, and then this. So the order filters of this poset, and if you tilt them appropriately, are nothing other than the Young diagrams, which sit inside of a 2x2 box. So in other words, what that tells me is that I can identify each element here of this original poset with one of these order filters. So let me just write the identification. This top one is 15, single box. So all I've done is I've just labeled according to this theorem or this fact that we're guaranteed that the order filters, the poset of joint irreducibles, exactly correspond to the original lattice. Okay. Any questions about that? So otherwise, just with this relabeling, everything still looks the same, or everything still should be the same as before. So let me do the following. So let me also just label these. Just so let's start with the simplest example. So let me consider, again, take the reason, so consider the indicator vectors. These order filters. So in the C4 case, I'll think of each box of my Young diagram as labeling some coordinate of R3. So I have C3, existing labels, coordinates of R3. And for example, I'll just write them this way. So 1, 2, 3. And so I take each one of these and I just write down the indicator vector of whether that element is present. So first one is 0, 0, 0, corresponding to this. 1, 0, 0, box. And 1, 0. Shape. 1, 1, plus. So fine. Anyone recognize these vertices as something? Okay, the standard simplex in R3. or at least one standard simplex in R3, and if you compute its volume correctly, you'll find that its volume is equal to 1. Okay. Fine.
What is the volume of the area of the triangle?
Sorry?
It's the area of the triangle.
Yeah.
Side times 1. Is it 1 or 1 half?
So you should take the normalized volume.
It's 1. It's the triangle has area 1.
All right, so maybe this one's a little difficult to sort of generalize from, but I'll leave that for now. Okay, those things. All right, so let me do the same thing for wedge 2 of these. All right, so here was my set of join irreducible elements, and then I have these. I'll just label these 1, 2, 3, 4. So this gives me labeling coordinates of 4. So empty set, box, box, box. This one and that. Right. So let's just write these down. So again, all I've done is I've taken each one of these as they sit inside of this poset, and I've written down the indicator vectors. This polytope may be a little harder to recognize, but these turn out to be the vertices of a pyramid over iterated pyramid over a square. Well, it's a 4-dimensional polytope. And if you compute its normalized volume, so again, each triangle should have volume 1. Okay, normalized for now. Okay, 2. So why did we look at this construction? Well, this 1 is also the degree of P3. And this 2 is also the degree of Simonyi 24. So GR24 is cut off by a unique quadric. P12 4 plus P14 P23 equals P13 P24. And so in this case, we've constructed polytopes whose volume is equal to the degree of the corresponding space from which we considered. So if you know a thing about Newton-Okounkov bodies, this more or less, assuming we can construct these in a kind of clever way to show that they actually come from the coordinate ring in some nice way, shows that these things are actually going to be Newton-Okounkov bodies for these spaces. Any questions about that?
Usually if I can forget about geometry if I just take a Young diagram, I choose a filling, I do this construction.
Yeah, so
What's that? What's that? A compute volume. And does it not depend on the filling? The labeling actually.
so it's not dependent. If you permute these, you'll just permute these around. So you act on your shape by some invertible transformation, which preserves volume. So you get the same kind of polytope, same kind of normalized volume, and all the same things.
What if I take just an arbitrary shape diagram?
Yes. So you can't take arbitrary shape. You have to take one of these k by n minus k rectangles. So that's the one in which all of the. But so let me say a little bit more about this minuscule case. Okay, so in general, so if you do this construction for GRKN, so what you find is that the weight of set equals the set of order filters of the k by n minus k rectangle Young diagram.
I guess the question is it authority for arbitrary shape?
Right, so if you take an arbitrary shape, it's not clear how this might arise as the weight poset of one of these things. But it turns out that for any minuscule, let me maybe say a little bit more about this minuscule criterion, but for any minuscule condition, you can get a poset. So there are some shapes which are kind of okay to look at, but in general, if you take this, you get some polytope, and maybe that should correspond to a Schubert, but yeah, that's not so clear. Okay, so in principle, you might hope to be able to run the same construction for any Schubert variety sitting inside of a minuscule space. And that would be the interpretation if you take an arbitrary Young diagram and try to do this.
Are you saying it's not the theorem? It's
Not a theorem, so I don't exactly know what happens for Schuberts.
But there's an obvious statement, right? The volume is equal to the degree of the Schubert variety.
Yes,
Is this true or false or not? No.
I don't know. So I'm not sure anyone has looked at this, I think.
Okay, basis of the Hebe torque, right?
Yes, I think that's right. Yeah, so. Right, so this is not the problem part. So, right, so here I just told you take a poset and then write down some indicator vectors, and I'm promising you that these come from some valuation.
Yeah.
And so you need to be a little careful when you construct this thing. So I think it should work out. I haven't checked it.
Okay.
So it's not a theorem that I know, but in principle, I think. So let me say a little more about minuscule.
For Grassmannians, this is the Gelfand-Zetlin story, right?
Yeah, this is equivalent to the Gelfand-Zetlin story. I mean, you can do it for any minuscule homogeneous space, actually. So,
It's the language of Hebe.
okay.
Hebe. Japanese name, Hebe.
who's called?
Yeah.
H. But the posets is Proctor and Stonebridge, right?
No, just the dates. It's around the same time, but the 80s.
Yeah, they classify the posets.
Okay, so this is the classification. Homogeneous spaces. So I'll just try to write them down. So GR and okay. Have Brownian Grassmannians. So sorry. Okay. Ordinal Grassmannians. Okay, there's some daily fine. One, put it in all. Seven, and then a few more, type D. So there's also 100. One, even. What did I do here? Okay, so there's a classification of these things, and Well, I've already said the Grassmannians correspond to these rectangular Young diagrams. Turns out that Lagrangian Grassmannians and orthogonal, these are kind of coming in pairs, and they're both labeled by staircase diagrams. Cayley plane has a kind of strange shape, so you can find what these two are. These are other staircase ones. And then these are something shaped like this.
So I would usually call the LG co-minuscule. Like the geometry is a bit different from the rest.
Oh, sorry, yes. Yes, okay, that's, sorry. Yeah, okay, thinking about another paper now. Sorry.
Did Cayley know about Cayley plane?
No, I think these are just named after Cayley. It's not clear to me what exactly the connection is, but Cayley was studying some octonians and then decided that they're quite similar, so named them.
It's the actonionic projective plane.
What's the subscript in the Katie thing? Does P?
So, oh, sorry, P6 or P1. So these are classified by their Dinkin diagrams. So, so 1, 2, 3, 6. So there are parabolic subgroups corresponding to these two nodes. So there's a Dinkin symmetry there, which is why you see both of them. And if you take the exceptional Lie group E6 quotient by either of these parabolics, you get something called the gate. So what I just told you, this whole story for the Grassmannians also works out for any one of these. So if you take any one of these kinds of shapes, you play the same game where you write down all the order filters, you write down the indicator vectors, and you produce similar polytopes. So whatever the analogous polytopes for these are, and they give you Newton-Okounkov bodies for these faces. So I just want to indicate, so this is one way in which you could mean that take other shapes of Young diagrams. So there's some skew shapes, there's staircase shapes, whatever you like. And in general, if you just want to take an arbitrary Young diagram, these might come up as Schubert varieties of these things, and you can try to play the same game. So the only part I haven't proven yet is that if you take a Schubert variety, you need to make sure that this actually arises as some kind of valuation on the corresponding coordinate ring. And you need to be a little careful there. Okay, so that'll be the second half of it. So yeah, I'll take any questions and then maybe pause for a few minutes before I start the next.
Okay, so questions and then maybe 5-minute break.
So just to make sure, in all of those cases, you have a toric degeneration because you have evaluation and
Yeah, so
the toric variety.
So you need a little more. So these polytopes, these are ordered polytopes for these posets. So you can prove they have the integer decomposition property, meaning that if you take any integer point in a dilation, you can actually write it as a sum of that many integer points below. So when you have that condition, then you also get the toric variety. You get a degeneration to that toric variety. In general, if you don't have that kind of condition, then maybe you only get a degeneration to something whose normalization is that toric variety. Yeah, but in these cases, it's very nice. You actually get a degeneration to the specific toric variety without any other operations you need.
The toric variety in question need not be smooth.
Right.
No, more than that, cannot be smooth,
Cannot be smooth. I see.
except when it's the same as
Yeah.
the variety you started with, and that happens in exactly one of these cases.
Because the cohomology ring is different. For example,
I guess that's true.
not generated in degree 1, for example.
Some rigidity of on a variety.
They would be like diffeomorphic if it was Smith.
Yeah, that's right. And then the cohomology ring will be the same, which we know is not the case.
Sorry, were we supposed to see like what, like the point of this is, or is that coming?
No, not yet.
Oh, okay, all right.
So I've just given a simple case of the construction I'll talk about later.
But what, okay, but even in these simple cases, like what
So the point is to get easy descriptions of Newton-Okounkov bodies for these spaces. So in general, if you try to sit down, someone gives you a valuation in a ring and asks you to play this game, you'll be quite stuck. And so in this specific case, there's a very nice way to compute it, and hopefully you can also extend it to non-minuscule things, but it's a little less clear.
Okay, so the point is getting that polytope, which is a Newton-Okounkov body. Okay.
Which you haven't
Which I haven't defined.
defined.
Okay, we'll resume in 5 minutes.
All right, so for the second part, I'd like to try to explain now where the instruction that I discussed before actually comes from. This might be slightly more difficult to follow, but nevertheless, hopefully it's understandable at least. So throughout this whole talk, I'm going to fix a few pieces of data. X, I, X. So this is some homogeneous space. Or let me not worry about the adjectives. Let me just say nice. Just so I can be sloppy.
Is it the same nice? Minuscule.
Not that nice. Right.
Simply connected, perhaps.
Yeah. Parabolic. So pi will be any dominant integral weight. Giving an embedding. The projected space over that reducible representation. And S will be a reduced expression for minimal coset representative of 0 and this parabolic spot quotient. So for the rest of the talk, I'll be fixing these 3 pieces of data, and I'll try to tell you how to use them to construct a valuation on the coordinate ring of this thing in such a way that, at least in the minuscule case, the Newton-Okounkov bodies you get are exactly the polytopes that I demonstrated earlier. Right. So let me give a brief outline the rest of the talk, and then we'll get to it. So valuations plus Newton-Okounkov bodies. Minuscule valuations. Maybe by example. And produce some non-minuscule. Also by example.
I'm not familiar with S. Well, I choose reduce expression to W0 and then like something.
So,
What do I do?
okay, so let's see. All right, so let me give one example of this. Okay, so for example, and let me just use the same one as before. So in W equals S4, this will be GR K4. Maybe if it, so W equals S4, W0, you can take many different expressions, but here's just one of them. Oh, no, sorry, S3. And then you look inside of this parabolic quotient, so W mod P, where this parabolic file group is all the elements you can get, all the words you can get without using a particular symbol function. So in this case, I not equal. So let me. P sub I is not equal, not yet. Okay, and in this particular case for GR24, I should write so low here. It's so visible. GR24, W2 equals all the words without the actual words. It's 1, 3. And when you take the quotient, you should then find the minimal length representative of this guy inside of. So let's see. Okay, let me just write it quickly over here. So equals. So I take this. 0 equals. And let me try to find one.
2, 3, 1, 2, probably.
Yeah, exactly. So.
You should be able to see the diagram. You should be able to just see it in the rectangle. Just by
Exactly.
boxing 3.
That's right. So the minuscule poset also gives you every reduced expression for W upper P by taking linear extensions. So if you label this properly by the unique simple reflection or Chevalley generator, which lowers the weight, then if you straighten this into any total order, so there are 2 of them, so straightening 2, 3, 1, 2, 2, 1, 3, 2. And there are 2 expressions for W upper P in this case, also corresponding with the fact that the degree of that Grassmannian is 2.
Is there a typo, like the W mod WPI is the set of generators?
Sorry, here is okay, yeah.
So,
For I is in
a
on it.
word.
Where I is in on it.
Before he was doing without,
Yeah, I is in on it.
Yeah, okay, yes. Thanks.
Depends on what I means. I think
Hopefully this-
Okay, yes, that's
it was finally,
If you-
See
if you
before.
know what it means.
Maybe this description is a little nicer. You just take the poset, you label it by the unique Chevalley generator, which lowers the weight, and then any linear extension gives you a reduced expression for minimal coset representative. Okay. Erase this. All right, so let me start here. So I'll first say not too much, but at least a little bit about valuations and Newton-Okounkov bodies. Let me give some definitions. What are these? So here A, finitely generated algebra. And for me, I'll just take it over C, but you can do it slightly more generally. And I'll just define it. So evaluation. On the non-zero elements of A. Rational number. Just any function satisfying these properties. So if you add 2 elements and then you take the valuation, it should be at least the minimum of their valuations. You multiply any 2 elements, and you should get the sum of their valuations. And then if you scale any function by a constant, you should just get the same value. So evaluation is just any function satisfying these properties. And then a few additional things. I'll also define the associated graded for evaluation. where f greater equals x is all the elements. This valuation is greater than x. Okay, and analogously for f greater than x. So this is called the associated graded. Algebra. I won't need to worry too much about this today, so I'm going to not say too much about it. But in particular, one thing that I might care about is this property called one-dimensional leaves. So nu has one-dimensional leaves. If each f x a has dimension of us. So again, these are, maybe this is some slightly technical condition that for the rest of my talk will at least always be satisfied. Oh, I just need this to state a theorem later on, so again, I'm not too worried about this. So the main thing I want to focus on is just the definition of valuation. So if you've never seen this before, we just want to construct some function satisfying these properties. Okay. Again, so another
Is
definition,
the definition you sum over all x and q or just specific ones?
all x and q. So mine is a Lansky basis. For a respect mu if this place there are new generates. So if you haven't seen this before, hopefully you have seen something called Grosvenor bases before, okay? So these things are generalizations of Grosvenor bases, and you can think of this condition as sort of generalizing this condition that the initial elements have to generate the initial idea. So this is exactly the analogous statement for these valuations, and call it a Chovansky basis if the images of generators generate the image of the ring and the associated gradient. Right, so again, this will be some, I'll just use this to state a theorem. I won't worry too much about it today, except to say that we give finite Chovansky bases in many cases. But again, I won't be too worried about this. So that's one of the main definitions of Newton-Okounkov body. So if A is positively graded, and I'm just 0 graded, then I'll define the Newton-Okounkov body as follows, or maybe not, I'll define it, but it is defined as follows. Delta A. So kind of a long definition, but it's the closure of the convex hull. The union I equals 0. So if you want to compute this Newton-Okounkov body, one way to do it is that you first look at each homogeneous piece of
What's Q?
Q is just rational numbers here.
Why do you have quotes around here? Why do you have quotes around graded after B?
So I just mean the images in this thing, but I didn't really define what GRB means because B is not necessarily a finite generated algebra, it's just some subset.
This is a subset of rational numbers.
Sorry, which thing is a subset of? Like the valuation?
Newton-Okounkov. Hold on.
But the valuations will be some rational numbers, and then you take the convex hull and then take the closure.
So this is an interval.
Sorry, okay, sorry. That's what you meant. Okay, sorry. Some B. Thanks. I was confused what I missed, but
Sometimes you do want to project.
right, yes. Sometimes.
But now your definition of GER is.
Yes.
No, but you want Lex
So you-
order or something. right?
Yeah, you fix a total ordering. Q in this case, I'll usually just take Lex ordering or, yeah, there we go.
So you fix it around Q to the D somehow.
Yes, that's right.
If you write A as a quotient of a polynomial ring by an ideal, how do we express this in terms of the ideal?
Good question. Yeah, so I'm not too sure how you express this directly in terms of the ideal U quotient by. Yeah, I don't know if this has an easy answer, but
Doesn't have an easy.
yeah.
It's easier if you have it as a sub, well, as you sort of hinted, a subalgebra. And it's maybe.
Is that A1? A1?
A sub I.
Oh,
So let me explain this definition. So first you take the valuations of the degree I part, the homogeneous degree I part of A. Okay, so that's the valuations. You scale them appropriately. So in principle, you might take a cone and project it down, but first I'll scale them all. And you take a union over all such valuations.
What is AI now? Oh, it's all great. So A is graded, but that's not the same as the valuation number.
Yes. I equals homogeneous. Part of I. A of degree.
So if A is generated by monomials, you can see it on the exponents of monomial.
So you just take the exponent vector and exactly. And maybe you can pick some term ordering on them. Right. So after you compute all these valuations, you take the convex hull. And then you may have some cases where you additionally need to take the closure in case these valuations try to run away from you. They may converge or may not converge. So in general, this definition can be very poorly behaved. So in general, V and maybe typically R very poorly behaved. And so few bad things can happen, so they may not be finite. Even worse, may not have finite volume. And then maybe the second one's not so bad, right? But they may not be polyhedral. So maybe you can try to imagine some kind of situation where these valuations converge to some things and you really get a truly round shape as opposed to something which is sort of nice and flat. So in general, they can be quite difficult to understand, but at least one thing is true, so this is how they manage. Make sure I get this thing. So Y is a projective variety. A is homogeneous coordinate ring. New equation on A. One-dimensional weaves. So in this nice case, it turns out you can at least say a little bit. Okay? So in this case, then the volume of this Newton-Okounkov body should be equal to the degree of Y, okay, inside of this particular projective embedding. And furthermore, if U has a finite Kovansky basis. Then this is a rational polynomial. And you have a toric degeneration whose normalization is the toric variety of that polytope.
Those things are true, but I don't think any of them are due to Coven on them.
Ah, okay, so
It's fine.
I see. So that's where I read this result originally, but maybe due to U in part.
A tiny part of it, but I think the main part is due to Coven, Kolansky, and Mother's focus stuff.
I see.
What does homogeneous coordinate ring mean?
What is homogeneous coordinate ring? So you take the homogeneous functions on this thing as a projective variety.
So are you choosing an embedding into projective space? Or
Yes. So for me, all projective varieties come with an embedding. So if it's not embedded somewhere, I won't really call it a projective variety. So just to be clear, I guess Y sits inside us.
So like the Y is a projective variety, is the homogeneous coordinate ring. That part is like no assumption. The only part that's an assumption is the one-dimensional leaves.
Yes, one-dimensional leaves, and additionally this finite Kovansky. I mean, in some sense, this is an assumption on A, saying that A can't be too bad.
But I mean, it's like a finitely generated graded. So so you're saying generated degree 1 or something? That's the assumption on A.
Yeah, Ethereum.
Well, you should was finitely generated over.
Yes.
Also, fine.
What?
Like the graded pieces don't grow too wildly.
But it's the finitely generated algebra.
With some nice grading. Positively graded, I guess.
Thanks. Any other questions? Okay. So in general, these things are kind of hard to come by, reasonable descriptions. And so I'd like to give, in our minuscule case, sort of nice construction of one of these things. But yeah, any other questions so far? So these are all the definitions I'll need for valuations and Newton-Okounkov bodies.
How reasonable is this, like this one-dimensional leaf construction? Because somehow one could imagine, like in your minuscule case, that could be because all the weight spaces are like one-dimensional or something like that, which would be a very strict condition.
Yeah, so it's not too bad. So for example, in this case I was mentioned earlier, if A is generated by polynomials, for example, it's a subalgebra polynomial ring, usually you'll have this condition if you take something related to, say, the exponent vectors of these things. So that's the case that I'll be working in for the rest of this talk. And so for my talk, at least, this is not a strong assumption. It'll always be true. But yeah, in general, it's maybe not so clear to me. If you just take an arbitrary valuation, what could happen?
Isn't it true if D is equal to the dimension of Y? Isn't it just automatically true then? I think I just thought this time.
Yeah, sorry, I just mean in this abstract setup. So I'm not talking about the context here, just if you take some arbitrary valuation on some.
That's absolutely true. Yeah, but I'm just really
Yeah, I think that is true.
supporting your assumption. This is not a strong assumption.
Ah, yes, okay, yes. Okay, any other questions? Okay. So let me now fix a little more data associated to these initial choices. And then once we have that, we'll use it to construct a valuation. So I'm also going to define a unipotent cell sitting inside of G. Okay, so I take unipotent and I intersect it with this Schubert variety, Schubert cell. Bruja cell, I guess, double Bruja cell. So I'm going to need this object and then as well as a forest inside of here. Just define Y did I label this reduced expression? No. Okay, so S, my reduced expression is S R L S R1 Y R L L Y and 1, where these AIs are non-zero. And Y is the exponential of a corresponding Chevalley generator. So Y of A, exponential of A. Okay, so need to define these additional things. So this is a unipotent cell inside of G. It's the intersection of the unipotence with the Schubert or Bruhat cell. And then this is an algebraic torus sitting inside of that unipotent cell, which I get just by concatenating the YIs.
In DL4, and I look at like the upper triangular 2x2 bit, the unipotent
Lower triangular.
lower triangular,
Yes.
and that's an affine space of dimension 4, and then I'm just looking at the non-zero coordinates, or are they mixed up somehow?
They're mixed up a little bit, but you can think of that as essentially the. Yeah, so the way I'll think about it is more directly in terms of these coefficients than the sort of how they get mixed up. So in general, if you draw this as upper, if you think of B plus as upper triangular, U minus as lower triangular with ones in the diagonal, then you just get some stars of the correct shape and then. Right, so what do I do with this? Well, we know that this is an algebraic torus, so if I take some, if I take some function inside of the homogeneous coordinate ring of X, my homogeneous space, then I can restrict F to this torus minus circ. And this will give me some Laurent polynomial in general. And the AIs.
I'm just a little confused here because U is like an additive. And so you ordinarily wouldn't find a torus sitting in an, I mean, the group operation on the torus wouldn't be compatible with the group operation on the additive group. Maybe that's okay.
Yeah.
I'm just like.
Yeah, so let me say explicitly how I think about these when I compute the valuation over here. So when I give you the valuation, it'll turn out always to be a polynomial. In fact, with a polynomial. And we get. And then you can do any number of things, but in this case, I'll just take the lowest degree term or lowest in some term order. So then define valuation of F to be, in this case, for example, you take the lexicographic order or if degree reverse lexicographic or any kind of thing. Then exponent vector. Of this restriction.
Why do you require the AIs to even be non-zero though? Couldn't the AIs just be zero? Wouldn't that be more? Then you would really be sort of getting the additive group. I mean, is there some reason you're making a lot requiring the AIs to be non-zero?
I guess not particularly. So you can indeed parameterize the additive group like that. And yeah, I guess that's fine.
What's Fi?
What's Fi?
What?
Oh, so Fi is the Chevalley generator. So let me just say these words too meaningful for some choice of SL2 city inside of G. So it's A. So if I go back to these posets earlier. So FIs are exactly the actions which send you down in this order. So maybe that's the way that I'll think about it today. So for example, F1 takes you from a vector of weight 1, 0, 0 to minus 1, 1, 0 in the Lie algebra.
So it's just like one sitting just below the diagonal.
Yes.
Is this? So the bottom is the coordinate for Schubert cell translated back to the. It's okay.
Yeah, so I think that's correct.
Okay.
Yeah.
Okay, then I know how to do it.
Right, so in principle, I've constructed something here, and in practice, it's not quite clear how to think of it just yet. Okay. So try to give this now. So the question is, how do we compute? This kind of restriction. In other words, you take an element of this form, you plug it into your polynomial and Fluker coordinates, and then you'd like to come up with some function in the AIs. So that's my goal for the next part of this. Okay, but any other questions before I go on? Okay. So if I work inside of some suitable completion of the universal enveloping algebra, I can think of these yi's. It's just the usual kind of Taylor expansion of some exponential. So 1 a I square over 2 square on. So if I take all these expansions and then I expand this whole thing out, I can produce something that looks like this. So u inside of these orders. Right. So this one's a L square over 2 L square over 1. 1 plus 1 around
F is a function on X or on G?
so yeah. Okay, so let me try to make sure I get this correct. So F is an element of the Lie algebra associated to G. So in principle, it's a function on G, and once I exponentiate it, it's definitely a function on.
Oh, that F is this F? I was asking about that.
Oh, sorry, this F here is a function on X. So that's so the right. Oh, maybe I should have called this P or something. Okay. So these F's are different. This is just some homogeneous function on X.
And X is G mod T.
Yes. X is G mod P. So some function, some polynomial in Fluker coordinates on G mod P.
And you're pulling back that to U
Exactly.
0?
Yes.
This, yeah. By restriction, you mean pull back.
Yeah, so if you take the quotient of this by P, it gives you an isomorphism with some torus sitting inside of G mod P. This thing is isomorphic to the big Schubert cell inside of G mod P, and so that's the sense in which I think of it as restriction, but in principle, it's pulling back. If you're
Or the image of.
yes. So we're in this case, and it's a little unclear what to do right now, but let me first define this. So first, we'll consider the case where this P here is some kind of projection. So I pick some weight vector, so the mu star G on V. So in principle, any coordinate function on X comes about in the following way. So you can pick some weight vector. So here, this is V mu. And then I just find the coefficient of V mu in the expansion of G times V pi into weight vectors. Okay, so if you want to actually look at this, so you go with action of G on highest weight vector, V sub pi, and then take the coefficient. d mu and the weight expansion. Okay. So there's one problem here, which is that in general, you may not have a canonical choice of weight basis for your representation, but let me kind of hide that under the rug for now. So you just pick some weight basis, so some basis of weight vectors for the representation. You expand the action of g on the highest weight vector in terms of your weight basis, and then you just take the corresponding coefficient. So it's like a Fluker coordinate, but for non-minuscule spaces, this is not quite well defined. So hopefully one can see the difficulty that's going to come about when I think about non-minuscule spaces. So I'll be a little careful about how I define this there, but at least for the context that I talked about earlier, this is fine. Okay. Right. Any questions about that? All right, so what do? Well, now instead of plugging in an arbitrary g, I just plug in an element of my torus. So phi of u. Well, 1 u pi.
Sorry, can I ask, like, is it necessary to have fi squared? Like,
Yes, so for the minuscule cases, so for the examples that I gave earlier, it doesn't matter. You'll see that in these cases, the action of the fi's can only be to the first power. So that's a property of minuscule representations. But if you take other if you take other dominant integral weights, you can in principle have arbitrarily large actions of these fi's. And so you'll need arbitrarily large powers in general.
okay, but how does that come into like this parameterization of u zero? Because I mean, fi squared is 0 there, right?
Fi squared is 0 if I'm working in a minuscule representation.
But I thought fi is just an SL2. Like,
Oh, so you should think of it inside. So yeah.
okay,
If SL2 acting on a symmetric power.
Right.
Look at SL2 acting by sim 5 or C2, then the lower triangular guy acts many times.
okay.
Yeah, so I don't necessarily want to write out a bunch of matrices of actions like this, but yeah. If you just take higher and higher powers of representations, for example, you can get arbitrarily long actions of these FIs.
Okay.
But this isn't really like a group action of an algebraic torus, because the group operation this is not compatible with the group operation of like torus operation.
Right. Yeah, so
Probably okay, maybe I'm just.
yeah. Yeah, so it's not so important for me now to think of this as a torus. Maybe it's sort of more important in a different context, but yeah, in principle, you just need this kind of decomposition of its elements. So this is what I'm going to be working with, and that's the important part. So it might seem a little hopeless, but let me write out a few terms of this expansion. So if you actually sit down and say multiply these all out, what you get is that every term is some homogeneous polynomial in the A's times some monomial in the F's. So let me write out just a few of these. So it starts off as 1 plus, okay, let me try to write this in general one time, and then I'll do specific examples from there on. So okay, so sum over R sub j plus I A j times F. Again, there's a sum over I here. Right, so here's one term of this thing. You can imagine next term will be some quadratic expressions. The A's times F sub J. I guess the ordering matters. So it's the and then U. Okay. So as you multiply this out, be aware that the FIs don't necessarily commute. And you act by this thing on V. So why is this a little bit nicer? Well, in some sense, I know how these monomials act on the highest weight vector. Okay, so if we go back to this picture, they just lower the weight by the corresponding path here. So the action of monomial F i's acts by lowering weight. So if you start at the highest weight vector, if you want to find out which one of these has a non-zero action, you just follow the path with the corresponding labels. So let me give a specific example now of how you do this computation for GR24. In GR24, I'm going to think of these coordinates as phi mu, phi mu star is mu times u12. And now I just need to look at which f's act by non-zero actions. So if there's no edge without label, then the corresponding f acts trivially. So let's start with this top one here. So example E0, 1, 0. E0, 0, which is just E12. Or U times E12. So when I look at this expansion, there's a unique term which gives you a coefficient of E12. It's just the do nothing action. Okay, so it's 1, and you get no other coefficients. Everything else sends E12 to some other combination of weight vectors or 0, and you won't pick up any coefficient for this. Okay, so the only thing you can do is take the 1 action here, just don't act by any FIs, and stay at E12. Okay. So let me keep going. So phi of 1 minus 1, 1, U1 dual, and U times E12. Again, the only way to get non-zero coefficient for E13 when you act on the highest weight is to only act by F2. So F2 on E12 gives me E13. Everything else gives me 0 or some other weight vectors. And so all I need to do is find the coefficient in front of F2 in here. So if I go back and I take my particular reduced expression, so this case was S. 3 S1 2 corresponding to the parametrization y2 4 y3 3 y1 2 y2 1. Right. There are only 2 terms here, which give me one F2. And so I get A1 plus A4. So in other words, when I expand this out, okay, as was pointed out earlier, I only need to think about the first powers of the F's in the minuscule case. So this is not too bad. The coefficient of F2 in this expansion is exactly A1 plus A4. Any questions about that?
mu is just something SLN. You, sorry, you.
U is just something of this format. So some products of these guys. So yeah, something in SL.
So you. Does you always look like this? In this example?
So when I think of it as acting on this particular representation on the second wedge power, it always looks like this.
So in the example, secretly, you, in the first example that you wrote, for the 0, what you do is you write U as this, and then.
That's right.
Oh, I see.
Okay. So if you act by the rest of them,
Are you saying you only get these linear terms, or are you just saying that like that's the only thing that matters?
these are the only things which act non-trivially on that representation.
But it's not that YT4 is just only.
Right.
Of A4
Yes.
is just the like. Constant linear
Yes.
term,
Yes.
you have initial.
Yes,
terms,
yes,
But they don't matter.
Yes.
If you were to write a matrices for that representation, the other products are just 0.
Yes.
Good.
Yeah. So that's a property of minuscule representations. It makes these expansions very simple. All right, so this gives you some questions. And let me just write out the rest of them. Let me do this. Okay, so 1 plus 4. One, 2. One, 2. 1 and 2 and 3. So if you take each of these weight vectors, compute the projection formula by this kind of restriction, you'll get these polynomials in the A's.
Sorry, could you explain how you got one of the things in the middle row?
One of these two.
Yeah, and why they're not swapped?
Why they're not swapped?
Yeah.
Okay, yeah. All right, so let's look at -1, 0, 1, for example. So there's a 2 here and a 1. So this says that you need to take the action which first starts with F2 and then uses F1. So that comes, oh, okay, sorry. I labeled them there. Thank you.
Good.
Yeah. Okay, so I take this first action by F2, I take this term here, I take this action by F1, and then I need to take 1 in the remaining terms. So I pick up a coefficient of A1, A2. Okay. So now I just follow the definition I gave earlier. Well, the valuation is, for example, I take the Lex min term of all these things. So I take this term, everything else is a monomial. I write down the exponent vectors, 0, 0, 0, 0. 1, 1, 1. And this is exactly the polytope that we wrote down earlier. So the whole point is that when you look at this action by these yi's, it corresponds to basically finding paths inside of the representation which have the corresponding labels. So using that translation, you can basically prove everything you want to about the minuscule case. So the key observation here, that computing these restrictions, the I, the mu minus circ is equivalent to finding same label okay, as polynomials. Yeah. That tells you exactly which coefficients you pick up, and that'll give you the way to express all of these coefficients. So you play this game for any minuscule representation, and you can then prove the following theorem. So for this particular valuation, mu and I guess the homogeneous coordinate ring of my homogeneous space. Then this Newton-Okounkov body mu is exactly the order polytope of the coset associated to. So to say that sort of in this example, if I take these order posets, the red elements here, I create the order polytope by writing down the indicator vectors, the order filters, then I get exactly the Newton-Okounkov body of this valuation.
That's your theorem.
That's my theorem. Yeah, so this is joint work with Peter Spacek.
We're in the setting of the theorem on the right.
Sorry?
So this is in the setting of this theorem on the right.
Right.
You prove that they have one dimensional leaves and
If every one dimensional leaves, we find a finite Hovansky basis. So turns out that you can use this order polytope description to compute the volume directly. So you have an inclusion of convex bodies, the smaller of which is the same volume as the larger one, they must be the same. So you can compute directly what the volume should be, and then you show that it's equal to the degree of that corresponding homogeneous space. So that's how this theorem is proved. So hopefully this motivates the construction earlier. So now you know that if you take any minuscule representation, you write down this poset, you write down the indicator vectors of order filters, you get a Newton-Okounkov body for that homogeneous space. Right. Are there any questions so far?
In your example, are these y? Do these y's sort of really multiply to an element that looks like sort of the box below the?
Yes.
Because if I was thinking, because like F2, for example, is like corresponds to like the second. So if A1 was 1 and say all these other A's are very close to 0, you get something that looks like it would have an entry maybe where it shouldn't have an entry.
So if you multiply this out in the GR24,
Yeah, just take all the other, imagine just A1 is the only one that's non-zero. That's what then you sort of get it. If A1 was the only one that's non-zero, oh, well, okay. But then what if F3 was the only one that was non-zero? If A3 was the only one that was non-zero, then might not you get something sort of below the diagonal there? Like if A3, if all the others were non, what is 1 plus A3 F3?
okay. I see. Okay.
I mean, this could be some group, but maybe it's not exactly that group is what I was thinking.
Yeah, so that's why I don't necessarily want to take the closure of this thing. So yeah, so if you let these go to 0, you pick some kind of closure of this unipotent cell, which gives you the stratification of G mod P into, I think, Schubert cells. But in principle, you need to let these go to 0. So I don't necessarily want to think about those, maybe, which is why I'm restricting to the torus here.
Is it possible to, since you already wrote a matrix, is it possible to write down the matrix multiplication of that expression for us? Just to be confident.
ask him to multiply forward for me.
So maybe after this talk, so there's only 10 more minutes. So I'd like to say a little bit about the non-minuscule case.
Yeah. Sorry.
Maybe I missed some part of the talk about that. Usually when people talk about like Okounkov bodies, they choose a flag inside their variety. What is the flag in this situation?
Okay, so I'm actually not too sure how these constructions relate. So it's sort of more geometric one where you choose a flag and then you look at the order vanishing among those. Yeah, I'm not too sure.
You expect it to be like the Schubert varieties for the suffixes of WP?
But he's also doing like a. It's a little subtle, like, when you take the min exponent vector, no, actually, that one's really good.
So
Can you also associate some Laurent polynomial here, which has to do with, like, it's like a superpotential for this?
yeah, so in a separate work, I've also used this idea to give a construction of a superpotential for any minuscule G mod P. So it's a little more difficult than this, but let me try to give a rough idea, and then in the last 5 minutes, I'll say something about the non-minuscule case. Let me make one observation here. Okay, so if we go back to the labelings of these by Fluker coordinates. So for some reason, maybe I just think of this monomial to begin with, and if I write it down in the torus coordinates, just A1, A2, A3, A4. Well, I can try to cancel this monomial by using other terms here. So if I look, well, if I take the single box 2, 1, then I get one of these terms, so A1, A2, A3, A4, but I also get another term A1 squared plus A2, sorry, A2, A3. And so if I subtract these two, I'll be left with this term here, which I could then cancel by multiplying these two together. So all I've done is just find out the Fluker relation that we all know about. So this is the standard Fluker relation if you subtract the, say, middle one. But the point is you can play this game for many other sort of monomials in the Fluker coordinates. You can try to find what the torus monomial is, and then you can try to cancel it out with something. And this gives you what turned out to be a rational function, which is the superpotential exactly for this space. So the denominators for the rational function are some generalized minors. And then to compute the numerators, you have to do a slightly different version of this game. But yeah, exactly. I can do exactly this kind of thing to produce superpotentials, and that's what I did in a separate. So if you know about this Reich-Williams result for Grassmannians, that the superpotential polytope, so they associate some polytope to the superpotential, coincides with this kind of Newton-Okounkov body. This is exactly the same story. So this is the Newton-Okounkov body that they show. And in principle, this lets you play the same game for any minuscule homogeneous space now. So you could try to establish the same result. This will be the analog of the rectangles cluster polytope.
They also do it for Schubert varieties.
Yeah, they recently did it for Schubert varieties as well, and I think you can play the same game here. And in principle, I think our superpotential result also extends to Schubert varieties.
Do you have an explicit formula for the spinor variety, the type D one?
Yeah. So we have explicit formulas for any minuscule homogeneous space.
Cool.
Any other questions?
Can I follow up that question? Do you have any cluster structure on that Fluker and the algebra from type D one?
So that's it. So I think essentially if you take the Geisler-Claire-Shor cluster structure, I'm not sure if you're too familiar with this. So the answer is a qualified yes.
Okay.
So it's a little difficult to work with. We gave explicit expressions for frozen variables for this thing, and you need to work a little bit harder to write down sort of actual cluster variables to write down a full seed.
But it's algebraic, you don't have like Playback graphs or.
Yeah, so there's some notion of Playback graphs or some networks for other types, but it's not so clear exactly. So in the last couple of minutes, let me say a little bit about the non-minuscule case. So earlier I remarked that if your representation is non-minuscule, then this first thing here, this dual vector for mu, is not quite well defined. So the reason for this is that general. So weight spaces may have multiplicity. And have dimension bigger than 1. And then it's really not so clear how you might choose sort of a basis for each one of these weight spaces. So there are many different bases. So the idea, which I don't have enough time to describe, but the idea is to choose a basis which is sufficiently compatible with the FI actions. The FI actions. And then you basically hope that you can do the same thing as in the minuscule case, that you can sit down, compute all these basis vectors, write down the projections onto those weight vectors, express them in terms of these kinds of expansions, and then get some polynomials. And I think it turns out, at least in many, many examples that I've computed, that you can play this game. So I've pre-drawn one more here. So here, X is SL4 mod E13. So this is the flag variety, FL13. So this is the flag variety, partial flag variety of one-dimensional subspaces contained in three-dimensional subspaces. I take my highest weight to be a sum of two fundamental weights, so phi1 plus phi2. And I take this reduced expression here for minimal coset representative. What I've done here is I've drawn a coset diagram, okay, where each node corresponds to a weight vector, and I've written the weight above it. So for example, this weight here, 101, it's exactly this fundamental weight, it's our sum of two fundamental weights. I've drawn a graph labeling the actions of Chevalley generators. So if you follow each edge, this tells you to act by Fi to go to the right or Ei to go to the left. And this is a particular choice of basis for which the graph looks like this. So these dotted edges are only one directional. So it turns out there's only an Fi direction, Fi action in that direction, you can't go back with it. So fine. So you play the same game where for each of these weight vectors, you compute the projection on, compute the projection corresponding to the, projection restricted to the torus. And that gives you each one of these exponent vectors when you take the Lex-min term. Right, so it turns out that this has a few nice properties. So its volume is indeed equal to the degree of this flag variety. Okay, so this gives you some hope that you can try to play the same game with some kind of Chevalley basis. So I called it a Chevalley basis. That's why we call these Chevalley polytopes as well in the non-minuscule case. And I'd like to highlight one more very interesting property here. I'll go over my few minutes.
I have no idea what I'm talking about, but isn't there like something like crystal basis that produces pictures like that?
Yes, but crystal basis doesn't quite work out. So if you take the definition of crystal basis, it sort of gives you the wrong combinatorics to play this game.
That's different basis.
Different basis. So it's quite subtle, the difference. So you don't see it for minuscule things, and even for many sort of non-minuscule cases, you still don't see these. That's it. But crystal basis doesn't quite work out.
get different polytopes that don't come from spin polytopes?
Yes, so. Okay. So I'd like to finish with just one observation here. So this flag variety kind of embeds into a product of two Grassmannians. So you can think of it as a GR1,4 and a GR3,4. And correspondingly, we have some polytopes for those over here. Okay, so these two standard simplices. And now let me embed them inside of the corresponding space in a kind of interesting way. So S3, S2, S1, S2, S3. Okay. So if I take corresponding reduced expressions here, I'll get S2, S1. And this one is S1, S2, S3. So I can identify these as two different subsets of these vectors here. So if I just take the vertices of the order polytopes I got from here and embed them in this kind of strange way, so first one will go to 0, 0, 0, 1, 0, 0. And you take a Minkowski sum of this convex hull plus another convex hull. 0, 0, 0. Oops. So I just embedded my two standard simplices inside of R5 in different ways. But you take the convex hull, you get exactly the convex hull of these vertices here. So equals. And let me just call it equal. Convex hull, so this polytop delta. So I think this is actually true in general. So anytime you can write your weight as a sum of fundamental, okay, you can always write it as a sum of fundamental weights, but when you take the expression, the resulting polytope is a Minkowski sum of sort of smaller polytopes coming from the fundamental representations. That's just one sort of very nice fact.
Why is the highest weight just type 2?
Sorry. Okay, so thank you.
Okay.
101.
You're constructing these spaces
I'm constructing these, yes.
in some standard way.
Yes.
There are several, so Chemnitzer has a paper where he talks about perfect bases, and there's several versions of bases that all have very similar combinatorics that aren't quite the same. If you've looked at that.
Yeah, so I couldn't make any of the ones that I found work. So it was a little tricky to try these computations, but I tried crystal bases and perfect bases and a bunch of these things, but none of them seemed to quite give the.
So you wanted to get a superpotential, that's the goal here.
So that wasn't the goal, that was a really separate project. And this was just a sort of, it's a different idea there. Yeah.
Do you know like the change of basis to the canonical basis? Like is your basis compatible with positivity in a sense? Do you know?
Not sure.
Maybe your basis is another perfect basis.
Canonical basis is the same thing as crystal basis.
Yes.
And perfect basis is something else.
Well, there's several bases that satisfy, like there's this Markovich-Volonin basis, which is somehow satisfies some of the same combinatorics as like the canonical basis, but it's not actually just the same. It's like the same in some kind of quotient type thing or associated graded type thing, but not quite the same. I mean, I'm a super expert.
So I think these perfect bases do not have the right combinatorics for this construction, but I couldn't find anything which did already. A little unclear.
You should give a name. Otherwise, we won't even remember.
So
Long face.
a name for it. No. These are named the Chevalley base.
No. Chevalley basis has a meaning in itself. Name it after yourself.
Has a meaning.
So you know how to choose
W
basis?
basis.
Do you know how to choose a basis for what context?
Yeah, so. Yeah, so I don't have a fully general construction. I know in kind of any example how to cook up the correct basis. So that's why it hasn't gotten a name yet. Maybe it's not fully developed. But in general, for any representation, I'm pretty sure that you can choose a basis for which this kind of nice decomposition property holds. And the point is that, maybe I should say again, so the choice of basis doesn't affect the Newton-Okounkov polytope or Newton-Okounkov body. Because in that case, you're supposed to compute all the possible valuations anyway. So the whole point of the Chevalley basis is to give you a nice set for which you can compute the valuations of some small number of elements. That was the case for which I couldn't make any of the existing bases work. You just take the crystal basis or take a perfect basis, compute its valuation, you do not get the correct polytope.
Have you tried for the parallel story for Schubert varieties at all?
Not yet. Yeah, so I think a lot of things go through maybe without modification. I just haven't sat down and tried it. That's all I have.
Okay.